Welcome. This video is about section 5.2 from the Brown IB-SL chemistry book, looking at Hess's Law. And Hess's Law came about because scientists realized that although we can measure the energy change for a number of reactions, whether they're endothermic or exothermic, some reactions are really difficult or impractical to measure experimentally. They might be really slow, like the formation of fossil fuels, or it might be really dangerous, like with explosive things. So instead, what we found, or what Hess found, is that you can find it indirectly by finding a series of steps or reactions that yield the same final reaction you're interested in. So this is much like algebra when you add up equations and you look at what's the net equation that's left. Same thing is true with chemical reaction. So Hess's law says the enthalpy change of a reaction is equal to the sum of the enthalpy changes for the individual steps. So that means you add up the positive and negative values for individual steps, and then you get one final enthalpy change for your final net reaction. So the starting and final conditions plus the reactants and products have to be the same. So you have to check and make sure if it's a gas, liquid, or gas, water, etc. So it has to match identically in order for this to work. Okay, so I've been looking at an example here with you, and as we work through this example, let me explain some of the techniques I use when I'm using Hess's law. First of all, I think of Hess's law as the flippy switchy law. I know, really high tech, but stick with me. What that means is you have to check the direction of each step and the molar amounts in each step to see that it matches the reaction you're interested in. So it says calculate delta H, or the enthalpy change, for the reaction S plus O2 equals SO2. So if that's a reaction I'm interested in, and I'm given the two equations down below to achieve this, I have to look at the first equation and see, does it contain the reactant or product I'm interested in, and is it the correct molar amount? Well, it has S, which is one of my reactants. It has O2, not quite the right amount, but it has it. And then it has SO3, which I don't need. When I look at the second equation, it has SO2, which I need, but it's on the wrong side. It has O2, which I may or may not need, and it's on the correct side. And it has SO3, which I don't need. So when I look at these two equations, the only way I'm going to be able to combine these two equations to yield the equation I'm interested in is if I flip the second equation. The first equation is fine as written. The second equation has to be flipped. So let me start by writing the first equation. S plus 3 halves O2 yields SO3, and that value then remains negative 395. And my second equation, when I flip it over, the SO3 becomes the reactant, the SO2 and the 1/2 O2 become my product, and because I flip the reaction, I switch the sign to positive 98. Now when I add up the reactants from both equations, I'm left with S plus 3 halves O2 plus SO3. And when I combine the products from both equations, I have SO3 plus SO2 plus 1/2 O2. I also go ahead and add up my values here. So 15 minus 8 is 7. So negative 197 is the delta H value I get when combining the equations. So to finish up then, I look and see if I have like terms on both sides of the equation, and I have SO3 on both sides, so they cancel out. I have 3 halves O2 and 1/2 O2, so that means the 1/2 O2 comes off each side, leaving me just a single O2, and when I rewrite my equation, I see I have S plus O2 yields SO2 with a delta H value of negative 197 kilojoules per mole. So sometimes when people were looking to use Hess's law, they still couldn't find a series of equations that added up. So this idea of the standard enthalpy of formation came about. And the standard enthalpy of formation is the change in enthalpy that occurs when 1 mole of the substance forms from its elements in their standard states. So standard states I think of as their normal states. So standard enthalpy of formation is going to be for a compound, something forming from elements in their standard states, 1 mole of it. That's because the heat of formation for an element is considered 0. since it would have formed from itself. So we're starting from, the start of time here, or however you think we came to be, that the elements were here. We're not going to worry about how they formed. So the heat of formation gives you an indication of the stability of a substance relative to its elements, because it's almost always a negative value, meaning the compound's more stable. So the bigger the negative value, the more stable that compound is compared to the elements making it up. Okay, so heats of formation are going to be negative values because they're giving off energy. Making those bonds makes it more stable. An exothermic process going on. So keep that in mind. So another trick is we can use the heats of formation for each species. Species is just a word for saying element or compound. For each reactant and product, all of them involved in a reaction. So we can use the heats of formation for each species and find the heat of reaction. Because again, the route doesn't matter as long as it yields the same balanced equation at the end. So if I know the heat of formation for all my products and I add them together, and I subtract the heat of formation for all my reactants, that should be the heat of formation or the enthalpy change for my reaction. Now a little later we're going to use bond enthalpy, how much energy it takes to break the bonds, and then we're going to take reactants minus products. So how do I know it should be products minus reactants? Well, what I keep in mind is I know that heat of formation should be negative because it's an exothermic process making more stable compounds. And so if I take a negative minus a negative value, if it's exothermic, then this should be the bigger value. The product should be more negative and the reactants less negative, and so when I take a bigger negative minus a smaller negative, I get a negative delta H, and indeed it's exothermic. But if it was an endothermic process, my products would have less energy released than the reactants that formed them, and so now when I take a smaller x minus a larger y, I get a positive delta H. So that's how I remember if I'm taking products minus reactants or reactants minus products. So let's take a look at an example. It says the heat of formation for these three substances are given. Calculate the enthalpy change for this reaction. So remember, I'm going to take the sum of delta H, got a little trouble with my H here, the heats of formation for my products, and I'm going to subtract the sum of the heats of formation for my reactants. So starting with the products, I have 3 moles of CO2 forming, and each mole of CO2 releases negative 394 kilojoules per mole, plus I have 4 H2O, and it's important to note that the state is correct, it's a gas, 4 moles times the negative 286 kilojoules per mole. So that would be my products, and from that I'm going to subtract the heats of formation for my reactants. C3H8 is just 1 mole times that enthalpy value is negative 104 kilojoules per mole, plus the heat of formation for 5O2, well, this one's an easy one because O2 is 0 since it's an element, so I don't even have to account for that one. So now I just plug and chug. So if I did my math right, I ended up with my products having a value of negative 2326 minus the minus 104 value, so really I'm adding the 104. So I'm coming up with a value of negative 2224 kilojoules per mole as my enthalpy change.